So in the last few videos, we've been talking about functions and domain. In this video, we are going to be specifying a certain type of function known as a linear function. A linear function. Okay, so how do we define a linear function? Okay, imagine that we have some xy coordinate. So we have some here, and then we imagine that it's going through. So let me draw the x and y coordinate system, or the Cartesian coordinate system, as some people know it. And now imagine that I draw any line that is very straight and it goes through any of these 2 points. Now, this is a geometric visual that we're seeing here. We are seeing what happens to this line, but there's no algebraic description of it. And what do I mean by this algebraic? I mean, there is no f of x, or I mean, there is an f of x, but how do we describe this function right here? And what we could do is that, okay, let's see how much this function is changing, right? And now let's see how much it changes. So it's going, we see that this function is going down by some value, change in y, and we also see it that it's also going, in the acceleration by some change in x. It's going down, it's going to the right. It's going down, it's going to the right. It's going down, it's going to the right. And so what we could do is that we could write this as a ratio. And this ratio we're going to call the slope of the function So let me write it here in green. And it's going to take the form, which is the slope of it, which is going to be the ratio of the change in y values over the change in x values, which of course is just the initial point, right? The initial point, and then we have some final point, and we're going to subtract the final point minus the initial point and the y component, and then we're going to divide that over the final x component minus the initial component. And this gives us you could also write it as y2 minus y1, and this is known as the slope of the function. Now, we know that the slope of this function touches some x and it touches some y, where the line intercepts the y as some b and it has some slope. So we could say that f of x, more generally, is the slope of this function times some x value that is going down plus some constant b that is touching. Let's do an example. Let's say we were asked to graph the function f of x is equal to 4x plus 3. Well, let's draw it out. So right away, you could also do the table chart, which works pretty well. So when x is equal to 0, y is equal to 3, because remember it's another way of saying y. When x is equal to 1, this becomes 4 plus 3. So when x is equal to 1, this becomes 4 plus 3, which is 7. When x is equal to 2, this becomes 2 times 4 plus 3, which is 11. And 3, that becomes 12, that becomes 15, and so on and so forth. Now that we have all these points, we could actually graph it. So when x is equal to 0, this is equal to 3, and when this is equal to 1, this is equal to 7. And of course, if we draw it out, it's going to have a very, very steep slope, Imagine, when we think of steepness, imagine like you're some dude trying to walk up, and you see, walking up a ramp like this is probably not very easy. Whereas if you were to walk a ramp like this, it's probably very easy. Or ideally, if you were to walk on a flat slope, it'd be very easy. But when you have to climb something like this or walk against it, it's very steep, so it's not very easy. This is another way we could define slopes. So now, imagine now that we go back to our slope. So we have the slope, which is m is equal to y2 minus y1 over x2 minus x1. And let's say that we wanted to evaluate the slope. So we have some initial condition x, or I guess y in this case, minus some y, which is y1, over some x minus some x naught, or some x1. And you go like, okay, let me separate some y. So we're gonna multiply both sides by some. So I guess let me do it right here, so it makes a lot more sense. You'll see what I'm trying to do in a minute. You're like, okay, I sort of want to give this y by itself, so we're going to multiply by x minus x1, and we're going to get rid of that, so now we have x minus some x naught of some initial m times the slope is equal to some y minus some y1. And this is known, so let me write it here in green again. This is known as the slope intercept, or the point slope intercept. Point slope intercept. And what this means is that we have some given point P, which has an x1 and a y1 value, and we are also given some slope. With just these two criteria, we are able to find an algebraic function that could best fit this data. And of course, it is given by the slope of the function times x minus that initial point x1, which also happens to be equal to y minus y1, which in this case is the 2 points that we picked times the slope of whatever the function is. So let's do an example. So imagine we have some point x1, which we're gonna make this 1, 1. So this is gonna be our x1, y1, and imagine we have some other point 2, 3, which in this case would be x2 and y2. What is the line that best fits this data? Well, using this information right here above, we're gonna figure it out. So for example, the slope, we gotta figure out the slope, which is how steep this line is, which of course that would be y2 minus y1 over x2 minus x1, which in this case y2 is 3 minus 1 over x2 minus 1, which in this case the 3 minus 1, that's just 2, 2 minus 1, that's just 1. So the slope of this line is 2. So you might be asking to yourself, okay, that's great, we have the slope, but what do we do now, right? So now, interestingly enough, you can use any of these points to graph the line. But let's do this one first. Let's say, now that we have the slope, we could say that, okay, y, right, let's pick point 1. So we're going to make this y1 and it's going to be x1. So we're going to say that y minus 1 times the slope, which is 2, times x minus 1, right? And then we're going to simplify this. Y minus 1 is equal to 2x minus 2. And of course, this means that we could, simplify this a little bit further. So we could say that y is equal to 2x minus 1. You'd be like, okay, that's great. But what happens when we use this point instead? Well, let's see what happens. So we're going to let this y, we're going to use these points. So y minus 3 is equal to the slope, which is 2, times x minus 2. So again, y minus 3 is equal to 2x minus 4. We could add 3 to both sides to get rid of it. So y is equal to 2x minus 1. And holy moly, look at that. These are identical. So the lesson that we can get is that it really doesn't matter what point we use. We could use any of these, and we could also use, well, we need to use both of these to find the slope, and then we could pick any of these to find the full line and what its intercepts are. And as you can see, the slope of this is 2, and it intersects at -1 when x is equal to 0. So let's sort of graph this real quick just to see what it would look like. So let's graph it real quick. It's the y. And of course right here, this is the x. X, when x is equal to 0, this is equal to negative 1. When x is equal to 1, that's just 2. 2 minus 1, that's just 1. So this is right here. And of course, when x is equal to 2, that becomes 4, that becomes 3. So this is equal right here. And we could also go a little bit backwards. And we could draw a full line. And this is our function f of x. But now, that's great. So now let's see what kind of slopes we could have when it comes to these linear functions. And we're going to do a bunch of these exercises a little bit later on, but we're just going to do a few things and explore around. So let's do another example. Let's say we have the point 4, 3. We have these 2 points, 4, 3. And we're also given the point 6, 2. Just for fun. See what happens, right? Okay. Give me the line, right? And I ask you, okay, I'm going to give you these 2 points, and I want you to give me the line that best fits these 2 points in an algebraic function. You're like, okay, well, let's do something. We're going to let this one be x1, y1, and we're going to let this one be x2, y2. Again, we could have done it either way, but I'm going to do it this way just to see what happens. What is the slope of this function? Again, the slope is just the way we saw on that graph. It is just the change in y, so that'll be y2, which in this case is 2, minus y1, which is 3, x2, which is 6, minus 4. 2 minus 3, that becomes negative 1. This becomes 2, which is equal to negative 1/2. Instead of negative slope, it means it's decreasing by a half. Now, which one of these 2 points do I want to use for my x and y intercepts? Well, honestly, I would go for either one, but I'm gonna go with this one because it has rational numbers and they're even, so we could divide easily by 2. So let's do it. So y minus 2 is equal to the slope, which is negative 1/2. You get that the sign does matter, so don't forget the sign. Times x minus 6, which of course, that's just negative 2. That becomes negative x over 2, which there's a 1 on top, but that's just writing the same thing. So negative times a negative, that becomes positive plus 3. And of course, I'm going to add a 2 to both sides to get rid of it because I want to have it as a terms of y. So y is equal to negative x over 2 plus 5. And this is the slope intercept. This is the point intercept form. And of course, you could also graph it. And I'm going to do that just so you can see what it looks like. So we're going to graph it real quick. When x is equal to 0, this is equal to 5. When x is equal to 1, this becomes negative 1/2. Negative 1/2 plus 5. So let me do that real quick. So that's going to be 10 over 5 minus 1/2. That's just 9 over 4. 9 over, this should be over 2. This should be 9 over 2, which is about 4.5. So that's around, right around right here. Actually, excuse me, this is 5. It should be right here. And it's going to go like this. And as you can see, it's the slope is, the absolute value of the slope is less than 1. So we could see that it's going to be decreasing, of course. It's going to be very not so steep, but also it's going to be decreasing because it's negative. Which you hear me talking a lot about negative and decreasing, but let's look at some ways we could actually rationalize some of these functions. So now I talked a lot about functions, but let's just see which ways we can clarify some of these functions. For example, let's say we have a function that the slope is non-negative, meaning that it's not negative in any way. What this implies is that if the slope is definitely non-negative, meaning it's not multiplied by negative 1. This implies that, for example, the slope is going to be increasing at some rate m. And of course, this rate could be 1/3. It could be 1 over 64. It could be 1 over 10 to the power of 64. It could be any real number, any non-negative real number in this case. and it would increase because it's non-negative. It doesn't matter. You could have a slope that's very, very close to zero, like I don't know, 0.000 dot 001. It would almost look like a straight line, but it's definitely increasing by some very, very tiny. It would definitely be changing by some tiny amount. You could definitely do a change in y over a change in x, and of course it would be very small, but it would be there. The second case that we have is non-positive, meaning that the value is, well, not positive. It could be negative pi. It could be negative 64 to the power of 2. It could be negative 128. It could be negative to 1 over, 100 million to the power of trillion, whatever. It's going to be definitely decreasing because it has a negative. It has this weird pesky sign known as the negative sign. It doesn't matter what value it is, it's going to be decreasing. But what about when the slope is 0? Well, let's look at the case, right? If the slope is changing, that means it's going to increase by 1 unit up, or any unit up, right? It's going to be some change in y over some change in x. But if there's no change in x, meaning there's no slope, or there's no change in y, that just implies it's going to be a straight line because it's not rising anywhere at all. It's not going up. It's just staying at the same level. Think of it as sort of climbing steps, right? You're going up the step by some change in y, and then you're moving, forward by some change in x, and you're moving up, and you're moving down, you're moving up, right? You're going up, right, up, right, up, right, up, right. You're increasing by some rate. Whereas if you're not increasing at all, but you're definitely moving to the right, that's great, but you're not going to go to the second floor when we need to go to the second floor. So in this case, when the m is 0, or the slope is 0, we just get a straight line. And of course, this straight line, it either occupies the y-axis at some point. It could be here, it could be here, it could be here, it could be anywhere. It doesn't really matter where, but that's just sort of the way we define the slope of some of these lines. So let's do an example, right? How would we define the slope of a function n of x, such as negative 3 over 8x plus 1? Now, what I'm asking you is just to look at the slope of this function. Is this function going to be increasing or decreasing? Well, it has a pesky negative sign there, so we know it's going to be decreasing, meaning that it's going to go down. What about some... Oh, I erased the 8 there. So what about something like 1 over 64x plus 3? Well, again, it's going to be increasing, although it's going to be very, 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 very slow, because we're, the slope of this is very, very slow. What about something like 6x plus 5? Well, very steep slope. Negative 3x plus 2. Very steep slope, but it's going in the down direction, so it's going to look something like this. What about this? Actually, no. Yeah, actually, let's do it. Minus minus, that's just positive 8, so that becomes this. So again, it's going to be increasing. But one really interesting thing about the slope is that you could actually define it as a rise over run. We are running, or we are moving in some x direction, and then we're rising up in some y direction. Some change in y and some change in x. This is what the slope is. We're increasing this amount by some change in y or a change in x. It's a ratio. So, for example, here we are running. I guess we are going down by 3 units. Not really a slope anchor, but you can see that we're going to go down by 3 units, and we're going to run by 8 units. So this would be the slope. See? Very, very slow. So 3, 8, and of course we could write this. And of course here, we are going to go down by 1 unit. Oh, excuse me. We're going to go here. Oh, I guess we're going to go up by 1 unit. Or in this case, yeah, you could go up by 1 unit. And then we're going to run 64, which I'm not going to do it here, but you can see that it would probably be some very, very not so steep slope. And ideally here, we're just rising 3. So run 1, rise 3. So 1, 1, rise 3, and it's a very steep slope, and so on and so forth. And that's sort of the way you can remember it. So let me just write here. The slope is just equal to the change in y over the change in x. And I'm going to do a bunch of exercises so it could be a little bit clearer. Whoop, meant to write 1. So now, let's do some examples. And now we're going to utilize some of all the skills we've accumulated of the point and the slope. So let's say we are given 2 points, -1, -3, and we're given the point 2, -3. What is the line that best intercepts this point? And how do we describe it? Well, we can label any of these, and of course I always do it whichever way, but whatever is easier for you. I'm going to do this one. We're going to say this is x1, this is going to be y1, this is going to be x2, and this is going to be y2. So of course the slope is defined as y2 minus y1, which is -3. So don't forget, this is very important. 2 minus, which in this case would be -3 plus 3, 2 plus 1, 0 over 3, which means 0. Uh-oh! We have a slope of 0. So if we look at some graph, right, we're going to pretend this is the xy coordinate, right? We're going to pretend this is -1. So let me do something real quick. Let me do it like this. It doesn't really matter. Right, let's plug these in. -1, 3. So -1, 3, 2, -3. Oh, look at that. And of course, the slope is 0. Because it's not increasing. It's just going through these straight 2 points, and they're horizontal. So let's do another example. Let's say we are given the point 6, 8. So let's do another example. So let's say we're given the point 6, 8. And let's do, I don't know, 4, 5. What is the slope of this function, and how do we describe it? Again, this could be y1, x1, y1. This could be x2, y2, which implies that the slope of this function is just going to be 5 y2 minus y1, 8 over 4 minus x2, or x1, excuse me, 6. This becomes -3. This becomes -2. Negative over negative, this becomes 3 over 2. And this is the slope of the function. Okay, that's great. But how do we write it in slope-intercept form? And again, we could pick any of these points, but I'm going to go for these two because these are very nice even numbers. So, y minus y1, 8 times 3 over 2x minus 6. This is going to be y minus 8 times, well, 3 over 2x. And of course, 3 times 6, that's 18. -18 divided by 2, that becomes 9. And of course, y is equal to, well, we're going to make this a little bit simpler. So y is equal to 3 over 2x minus 1. Okay, so now let's graph this and describe it. So when x is equal to 0, this is equal to -1. So when x is equal to 1, this becomes 3 over 2 minus 2 over 2. Well, this becomes 1/2. So when x is equal to this, it becomes 1/2. When this is equal to 2, 2 times 3, that's 6. 6 divided by 2, 3. 3 minus 1, that becomes 2. So it goes right here. And as you can see, we are rising 3 and running 2. So we could draw the line. And it looks like this. It doesn't exactly look like that, but that's sort of the way you can remember it. Because again, we are running 2 and rising 1. So this would be the change in y, and this is the change in x. Ideally, you could repeat it by run 2, run 1, run 2, rise 3, and you could walk backwards, run 3, and this will give you the slope of the line. And as you can see, it's non-negative, which means it's going to go up, and we have a y-intercept of -1. Now, what happens when we have lines that sort of intersect? And again, this is just review, but let's think about it for a minute, right? Imagine we have some Cartesian coordinate, again, x, y. And now imagine we have two lines who have different slopes, so the slopes are not the same. So the slope of one is not equal to the slope of the other. So, okay, well, this one's, let's say it's going to go through this one. And this one's going to go through, let's say it's going to go through this one. And they touch some point P. And this right here is the point of intersection P, X, Y. And of course, we think to ourselves, okay, how can we find this point of intersection? Well, this is what we call a system of linear equations. And what that means is that we have some function f of x is equal to slope 1 times some x plus some constant, and we're going to say that the other function is some h of x, because it's different, has some other slope times some x plus some constant c. And of course, if we want to find what makes them equal to each other, we just set up the equation such as that f of x and h of x are equal to each other. What do we mean? Let's say we have the function y is equal to x plus 2, and we also have the function y is equal to 3 over 2x plus, or I guess let's do something easier. Let's do something that's nice. 4x plus, let's do 3. And we want to find out at what point do both of these have the exact same y value, meaning at what point do they intersect. So if these both have the same value, that means they have the same x value at that point. So this right here has the same x value, and of course here it has the same y value. At this point, both of these do. So we can make them equal to each other, which means that x plus 2 is just equal to 4x plus 3. Now, of course, this implies that, well, we want to have x in terms of everything. So this is going to go that way, that's going to go that way. So then we're going to have, okay, we're going to subtract x, and then we're going to subtract 3. So we're going to have -1 is equal to 3x, which implies that x is equal to -1 over 3. Right, because we subtract 2, that leaves us 1, we subtract 3, we have -3. So the common point of intersection is x is equal to -1. And sure enough, if we plug all of those in, so y is equal to -1 over 3 plus 2, right, we're going to plug it into here. We're going to get, well, that becomes 5 over 3, pretty nice. Let's plug it into this one, so this becomes y is equal to 4 times -1 plus 3 plus 3. This becomes -4 over 3 plus, well, 3 over 3, so that's going to be, well, 9 over 3, which equals 5 over 3. And sure enough, they do. And that's how you find the common points of intersections. Again, you could do it for anyone, but let's do another example. Let's say we have the function y is equal to -3 over 2x plus 6, and we have the function y is equal to 2x minus 2. At what point do they intercept? Well, one strategy you could do, which you could do, but it's very hard to do it geometrically. Sometimes it could be easier to do mathematically. But of course, we could sort of graph this one, which means that this would be -2. Keeps rising, again, rise over run. We run 1, we rise 2, and of course it will look something like this. Again, not accurate, but which is sort of the point. It's very difficult, especially in my handwriting. This one's going rise over run, so this is going to go down 3. So when this is equal to 6, It's going to go down 3, run 2. So it's going to go like this. Rise 3, run 2. And it should look something like this. And they touch at some weird point, which I don't know what this point is. Question mark, right? Some X coin. And it has, of course, the same Y value, which is sort of the reason why this works, because they shared this point. They are in the exact same point in the exact same time. Not really time, but sort of the exact same position. So, how do? We make them equal to each other. So, negative 3x plus 6 is equal to 2x minus 2. And, of course, we're going to move everything, so that means that negative 3 2x is equal to 2x minus 8. We're going to subtract 2x from both sides, which means that this is, okay, so then we're going to 6 over, this would be 4 over 2. So let me give me a minute, because 3 plus 4 over 2, this becomes 7 over 2x, which means that this would be, again, this is the way of doing it, 7, 2x is equal to negative 8. Both of these have negative, so they cancel out. So 7 over 2x is equal to 8, which implies that we can multiply both sides by 2. So we get 7 is equal to 16x. Don't forget the x. I'm running a little bit fast here. 16. And then we divide by 7, which means that x is equal to 16 over 7. And this would be the common point of interception. And again, you can verify this is true by plugging it in. But for formality, I'll do it. Or maybe actually I won't, because I'm seeing that these are not so fun numbers to work with. But you can verify that this is true. But now, let's do something a little bit more extra, I guess. That's something a little bit more challenging. What happens when two lines don't actually intercept? How do we know that? Well, if you think about it, right? It's such a very easy way to think about it. Imagine we have two straight lines. And these two straight lines are touching at some y-intercept. One is going this way. And of course, one is going the other way. Right? We're going to pretend these are exactly straight lines. Because if they're, if you guys don't believe that my lines are straight, then this won't work. The magic will go away. So, okay, the slope of this one is 0. The slope of this one is 0. And as you can see, since they're straight lines, they will never intersect. But look at the slope of this one and the slope of this one. They're exactly the same thing. Okay. So what happens when we have something that, for example, let's say we have two things. Say we have another example. Right, and this time I'm actually going to be methodical about it, so because I want you to see it. Or I guess let me do it like this. Let's say that this function, let me make it a little bit nicer so it actually makes a lot more sense, I guess. So imagine we have some line that is, we're going to have a slope that's, this one's run, so rise over run, so it's going to rise 2, run 2, or I guess it's going to rise 1, run 3, rise 1, run 3, rise 1, run 3, and of course you can keep going, dot, 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 and you draw the slope of this, and it looks something like this. Now you could draw it out. And of course, let me do the exact same thing, and I'm going to shift this line by some constant b. So I'm just moving it up. I'm just legit just like copying it and pasting it, and I'm moving it up by some constant b. What does this mean? Well, if I'm moving it up, it's going to be rise over run. So it's going to run 3, rise 1, run 3, rise 1, run 3, rise 1. And of course, what you could do here is that now you could sort of connect the lines, and now we have a line that connects it. And these lines are called parallel lines because they have some constant m slope. And as you can see, the slope of m1 is equal to the slope of m2. So now, what does this mean? What this means is that when you have the slope of one line that is equal to the slope of the other, they're called parallel lines. And of course, when they're parallel, that means that they will never intercept no matter how infinitely apart you are. It doesn't matter if you go from 1 to 2 to 3 or if you go to 4, or maybe you go to 6, and you might go to 7, you might go to 8, or you might go to maybe infinity. It doesn't really matter. You could keep going infinitely, and they will never touch because they have the sort of the same slope. But, and a big but, if the slope is not equal to each other, so if the slope is not equal to 1, or the slope is not equal to the other by any number, they will touch eventually. That's sort of, they have to be exactly the same, identical. No buts about it. They have to be. 1 is equal to 1 and 2 is equal to 3. 1 does not equal to 2. 1.1 does not equal to 3, and 0.0, or maybe I guess 1.000 ... is not equal to 1. Alright, it doesn't matter, so they're not equal. They have to be identical. Now, let's do something interesting, right? We've been doing a lot of line crossings, right? Okay, we have some lines that cross, but let's say we have some lines such as the y-intercept, right? These two lines, right? We have the y-intercept, and then we have the x-intercept that, these two lines cross each other. And that's pretty nice. But what if I wanted to have two other lines, right? Our own line instead of the y and x intercept, if that makes any sense, because these are the y and the x, right? We have some slope. And then we want this line to intercept with another line that has a slope such that they make a right angle. These two lines are orthogonal, or I guess you could say perpendicular. I like using the word orthogonal because it's easier for me to pronounce and makes me sound like smarty pants. We're going to say these two are orthogonal. So, what if I want some line, for example, to cross another line? Not necessarily this one, so let me erase these, right? So, let's say I wanted to cross, I have this line with some slope 1. And then it crosses another line. I'm trying to do this as best as careful, but we're going to pretend that these are exactly orthogonal. Again, every time I mean orthogonal, I mean perpendicular, such that these two make a right angle. So we have slope 2. So how do we find that? Well, one way I like to think about it, and sort of the way it's defined, there's a reason why it's defined as this, but we want the slope of the other one, the slope of 1, to be equal to the negative reciprocal of the other slope, which is going to be 1 over m2. Which implies that m1 is equal to m2, which is equal to negative 1. And this is sort of the condition to make orthogonal lines like this. These are lines that, for example, when you have the two slopes, they will cross each other. And it's sort of a special crossing because instead of being some weird angle between them, the angle between them is 90 degrees or orthogonal. So now, let's do an example, right? Let's say I have the line y is equal to 8x, right? Or I guess the slope of y is equal to x. So we're going to say that the slope of y is equal to x. So the slope of 1 is equal. What must the slope of another line be such that when they cross, they are orthogonal to each other? Well, following this formula, we could say that the slope of 1, which is 8, times the slope of 2 has to be equal to negative 1, which implies that the slope of 2 has to be equal to negative 1 over 8. And of course, you could sort of verify that this is true by plugging it in, and you will get orthogonal lines. So we're going to do a little bit of exercise with orthogonal lines. So let's pretend that we have some line y is equal to, let's say y is equal to 3 over 2x plus 2. And we want to find a line such that it's orthogonal to this line. Okay, well, let's think about it for a moment. So we care about the slope. So let's focus on the slope. So we're going to make the slope 1. And what the statement are for orthogonal lines or perpendicular lines is that m1, or the slope of 1 times the slope of the other one, has to satisfy equal to negative 1. They must satisfy this condition. We already have the slope of this one, which is 3 times the slope of 2 has to be equal to negative 1. And of course, by doing some simple algebra, we could figure out that the slope 2 has to be equal to negative 2 over 3. And of course, in this case, the intercept won't really matter because we could sort of draw it out like this. And this will be, okay, rise over run. So it's going to rise 3, run 2, rise 3, run 2. So boom, boom, boom. It looks like this. Where this one is the opposite, we're going to go down by 2. So we're going to go down by 2. Let's pick here. It doesn't really matter where you start. We're going to go down by 2, run 3. So let me go here and here. We're going to go down and run by 3. And of course, oh, look. You could sort of kind of see it already. So let me draw these actually with some straight lines. You could verify for yourself. So give me a minute. Okay, so I drew some lines and look, the angle right here, it's 90 degrees. Isn't that great? We did something in math today, guys. We figured out how do we make an angle such that it's 90 degrees. And that's pretty much it for linear models. There isn't really much more to it than that. You can have a system of linear equations where they intersect. You can have multiple. But that's all of what we care about. So, overall, let me do some overall remarks. So, we have a line. And this line is changing or rising or has a slope that is some change in y or so there's some change in x. It's rising or it's changing in the y direction and in the x direction by some constant or some amount. And in this case, it's just some y2 minus some y1 over some x2 minus x1, which is some rise over run. And of course, this slope, once we find the slope and we have some given points, we can use it to find the slope-intercept form, which in this case is the slope of the function plus some constant b. And in this case, this is known as the y-intercept, which is where it touches. Ideally, if we are given 2 points and we are asked to find which line fits these 2 points, we just need to use any of these 2 points to find the slope as given by the slope formula. And then we could pick either x2, y2, x1, or y1 and plug them back in to find this line that best fits it. But what if instead we have 2 lines that intercept at some point? What is the point of interception? Where, of course, the slope of one is not equal to the slope of the other. Then what would that mean? Well, we just make them equal to each other and then we solve for x. And of course, if they have the same x, then they must have the same y because they intercept at one point. What if we have lines that, for example, are parallel? Well, parallel lines never intercept. And how do we know they're parallel lines? Because the slope of one is equal to the slope of the other. They have identical slopes. Identical, exactly the same. What if the slopes are not identical, even by a fraction, even by a very infinitesimally small amount? Well, they must intercept at some point. But what if the slope is not this? What if the slope is 0? What if the slope doesn't do anything? Then it's just a flat line. It doesn't go anywhere. It's not going down or up, so it's just staying the same. It's staying at the same level. So what if instead we wanted to find 2 lines that intersect such that they're orthogonal to each other? Well, then the slope of one times the slope of the other must be equal to -1. That's the way that these are called orthogonal lines. And this is pretty much just a basic review of linear functions and some of their uses.